Hello everyone, I'm Tianxin from ETH Zurich, Applied Crypto Group. I will share with you some interesting findings about MongoDB secure encryption. This is a joint work with Zichen and Kenneth. So you might now be wondering what exactly are MongoDB and QE. To provide some context, MongoDB is a non-SQL database system known to be efficiently handling large-scale data. Queryable encryption extends MongoDB to enable encrypted searches. Introduced in June 2022, QE is the first searchable encryption technology available in a widely deployed database system. This was indeed exciting news for the research community. We were so curious about QE that we conducted an independent security analysis. To better understand our findings, some background knowledge is essential. Let's begin with a toy example of a MongoDB database. Imagine we're storing plain text employees data at the Springfield nuclear power plant. Interestingly, this power plant only has two job roles, the nuclear technician and the CEO. Our database is quite extreme, that contains data for just 3 personnel. So in a MongoDB database, a record is represented by a JSON document. Each document contains multiple fields and has a unique document ID. In our example, every JSON document has a name, job, and address fields. So the first document is a record of Homer Simpson as a nuclear technician. For the job field, job is the field name, and the nuclear technician is a field value. The second document is Lenny Leonard as the nuclear technician, and finally, the third document is the CEO, Charles Burns. Suppose we want to conduct an equality searches on the job field. A linear scan is clearly inefficient. Instead, to accommodate fast searches on the field values, a common approach is to incorporate an inverted search index. So this index stores searchable field values along with their corresponding document identifiers, or doc ID, which are used later for the document retrieval. In our example, nuclear technicians is stored along with doc ID 1 and 2, CEO is stored with doc ID 3. So this is good so far. However, since we are working with plain text database, so there's no privacy yet. This brings us to queryable encryption, or QE, an encrypted version of such a MongoDB database that allows us to conduct equality searches on the encrypted field values. So MongoDB claims that the QE adds another layer of security for your most sensitive data, where data remains secure in transit, at rest, in memory, in logs, and in backups. So this is truly exciting, as now we have efficient encrypted searches in a widely deployed database system. So since MongoDB is the 5th major database vendor by market share, with more than 43,000 business customers, if MongoDB's security claim about QE holds up, then it will have a far-reaching impact. You may be familiar with cryptographic primitives such as private information retrieval, fully homomorphic encryption, or oblivious RAM. However, QE does not belong to any of these categories. Instead, it is a searchable encryption scheme that allows some information leakage for efficiency. Because we are researchers in this particular field, we were a bit skeptical about their security claims, especially since there is no white paper or security proof around. To be able to continue our security analysis, we need to know how QE works. We were able to understand QE's inner working through reverse engineering their public code base. It's a complex scheme. So this is a figure directly from our paper. You can see the token derivation algorithm is already quite complex. To save you hundreds of hours digging into their code base, which we did, I'll give you a simplified overview of QE. So QE has an encrypted search index called ESC. You can interpret ESC as a dictionary. Specifically, ESC stores in the dictionary key field the PRF outputs of field values concatenated with a counter. This counter is called a document counter that tracks the number of document insertions with this field value. So in the value field, ESC stores the encrypted version of the document counters. So for nuclear technicians, counters 1 and 2 are stored. And for simplicity, I will omit the case for CEO. So next, we need to access encrypted documents. This is achieved by applying a PRF on the document counter and stored along with the documents. Because the PRF values are deterministic, so this can be used for searches. However, there's an issue with this approach. The ESC grows linearly in the number of document insertions. So in practice, we certainly do not want this linear storage blowup. So that's why QE introduced a specialized procedure called compaction, which is used to reduce the ESC size. So before compaction, for each searchable field, each document insertion will incur 1 document counter inserted. While after compaction, only the maximum counter is stored at a dedicated position. So as you can see, 2 is stored for nuclear technician here, and 1 can be recovered from 2. So incrementing the counter for each document insertion, so the PRF output used for retrieving documents is different, even for the same field value. So this is the standard technique of searchable encryption that provides snapshot security. By snapshot security, I mean that the adversary even have access to the snapshot of the encrypted database, still learns nothing about the underlying data. So sounds great. But implementation is usually more complicated than theory. So I haven't talked about how QE is implemented in MongoDB yet. Well, let's look at a specific file that implements QE's core read and write functionality. So 24 out of 29 are native MongoDB library headers. So indeed, QE is built using native MongoDB operations. Therefore, QE interacts with other MongoDB system components, such as caching, logging, and backups. MongoDB adopted this approach integrating QE is because it is cost-effective and incurs minimal changes to the existing system. So we need to emphasize this type of integration plays a crucial role in our analysis. So especially by examining the QE's interactions with other system components, we found a problem. The observation that these interactions may cause issues is also hinted by Grubbs et al. In their paper, Why Your Encrypted Database is Not Secure. So in our case with QE, we identified the problem in the logging system. MongoDB's logs allow us to mount query database reconstruction attacks. So I will focus on the operational log or op log here. You can find the attack using query log in our paper. So in real-world MongoDB applications, to mitigate the risk of single point failures, multiple database instances, often referred to as a replica set, is used. Similarly, QE must be initialized with such a replica set. So oplog records every write operations performed by the server and plays a crucial role in keeping these databases in sync. So you can see from the function here, this specific QE function directly calls MongoDB's oplog used for replication. Then, what does the oplog look like? Well, it's a mess. But looking at it closely, you can find it records information related to the MongoDB query operations. And what does the log tell us? Unfortunately, the information leakage about the queries and the data. Essentially, by grouping the logging transactions under the same transaction ID, we can learn which encrypted documents share the same field value. So in our example, edoc1 and edoc2 share the same field value, while edoc3 has a different one. So while the actual leakage extraction is much more complicated, and you can refer to our paper for more details. So this leakage that we can extract from oplog corresponds to the frequency and correlation leakage. By accessing to an auxiliary distribution, say knowing there are 2 nuclear technicians and 1 CEO, we can recover the underlying data. So we fine-tune the attack techniques based on Gui et al. For relational databases. So as you can see here, the correlation between jobs and the class of jobs can be exploited. So in our experiments, we use American community person level microdata. We use the 2012 dataset as the auxiliary information and the 2013 dataset as the recovery target. Because it took days to build a fresh QE encrypted database, we had to work with simulated leakage as we need to repeat our experiments multiple times. Although the leakage extracted from the op log is more noisy compared with query log, we managed to have a relatively high recovery rate. Next, you might be curious how and when to get this leaky op log, making our attack feasible. Well, this op log is on the server's file system, so really convenient for the snapshot adversary. So the only assumption that we make is a compaction procedure is performed. And this assumption is also quite reasonable. In fact, MongoDB currently recommends running compaction once the search index exceeds 1 GB. And in our experiments, we found that after inserting only around 650K documents, the size hit the 1 GB threshold. Finally, to wrap up my talk, I'd to leave you with some key takeaways. So what exactly went wrong with MongoDB's QE? So the vulnerabilities we found stems from QE's interaction with the logging system. This means that when designing a searchable encryption scheme, we can no longer view it as a standalone entity, but need to take into account the interactions with other system components. In addition, the specific leakage, we can extract results from the low-level implementations, for example, by exploiting transaction IDs that are seemingly benign. So we hypothesize that there is a communication gap between the designers and the implementers of QE. So therefore, ensuring effective communication between these two groups is essential. Thank you for your attention. Now I'm happy to take your questions.